We're going to look at what happens in a diode now if we change the signal slightly for a diode that's already forward biased. So we're not looking at what happens when we have an AC voltage that changes plus to minus and turns the diode on and off. We're actually looking at a small variation in signal that happens that does not change the bias point, but will actually vary the value of the circuits somewhat. So the small signal models create a way to make a linear characterization out of something that's nonlinear. So what we do is we take the derivative of the transfer function at the point where the Q point is, or the operating point. And if that's done, we can actually find the change of output diode current for a small change in voltage, which can be really useful. This is the same process we'll use later when we deal with transistor amplifiers. So if we have a diode operating at a particular point, at the Q point, and we take a tangent to that, the slope of that tangent is actually 1 over the resistance of the diode in the AC mode, or at that point. There are other resistances that occur at different points, but this is the resistance at that point. So when we bring a signal in, you notice that signal is varying slightly, and the output current is going to vary more, but you notice that the diode never goes into a reverse biased situation. It stays forward biased the whole time. And we can actually find the slope of the tangent line at that Q point if we want, and we can find the inverse to give you the small signal resistance. But can we find that value without graphing it? And the answer is yes, we definitely can. So let's look at a point, and this is just a random Q point on a curve, and we're going to assume that the eta value is 1. And we're going to write out the diode equation in its normal form, because we really don't know where on the curve we are, so we can't assume the diode voltage at this point. And the first thing we're going to do, because we have a tangent line means a derivative, so we're going to take the derivative with respect to voltage of that current curve, and we get IS over VT, e to the VD over VT. And that is actually equal to the conductance. That is the slope of the line not inverted. The conductance is equal to ISE VD over VT again. And if you look back at the original equation, you can see that the original equation has that component in it, just subtracting IS from it. So if we took IS and put it on the left side of the diode equation and had ID plus IS, it would equal ISE to the VD over VT. So we can substitute that in, and because IS is so much smaller than the diode current, we can actually approximate and say that 1 over the thermal voltage times the diode current is equal to the conductance. The resistance then is just 1 over the conductance, which is approximately the thermal voltage over the diode current. And we use 25 millivolts to assume that we're at room temperature, which means that in this case, you're finding the AC resistance using the DC circuit value. The DC current is what determines the AC resistance. It's probably the only time that you will be dealing with an AC value that comes from a DC value. So what we can do then in a small signal circuit is we can replace the diode with its small signal resistance. And because of the way the circuit is designed, the DC current will determine what that value will be. So in looking at an example, we have a 10 volt DC source that has a 1 volt peak ripple at 60 hertz. And we put a diode in series with a 10 kilo ohm resistor and the source. And then we want to find the DC voltage, the peak AC voltage across the diode, and using the following specifications. So we assume the diode has a 0.7 volt drop at 1 milliamp. So we're going to use superposition. First of all, this is what the circuit looks like. It's just an AC source in series with a DC source. So we're just modeling that ripple as a separate source. And using superposition, we're going to find the DC values first. So we're going to ignore the AC part, and we're going to figure out what the diode current is just by taking 10 volts and subtracting the diode voltage and dividing by 10K. And we get 0.93 milliamps, which is close enough to 1 milliamp that we actually don't need to do any more iterations. So we don't need to use iterations here. Our initial assumption was good. Now, we're going to calculate the resistance, and we take 25 millivolts divided by 0.93 milliamps, and we get 27 ohms. So what we do is we now replace that diode and put the AC source back in, and we end up with a resistance and an AC source, and now we can just use voltage division to figure out the voltage across the diode. If we do that, we get 2.7 milliamps for that value. So that's how small signal diodes work. The next topic I'm going into is completely unrelated. It just didn't fit anywhere else, so I put it in here because this was kind of short without it. So Zener diodes. Zener diodes are a diode we haven't talked about yet. They're diodes that are designed to be used in reverse bias. They are PN junction diodes that are highly doped on both the P and the N sides. And the mechanism that's used for the reverse flow is different than the avalanche breakdown that happens with normal PN junction diodes. So the diode can be used in reverse mode and it doesn't get damaged. In a Zener diode, the way the conduction and energy levels work, the conduction and valence levels work, at the junction, because the high doping on both sides, electrons actually can tunnel through that border or barrier. And the nice thing is it doesn't harm the diode to do that. It just happens, but it doesn't harm it. The forward bias drop is still around 0.7, so that doesn't change. But the reverse bias is actually a wide range of values. So you can have 5 volts, 12 volts, whatever. They can be used as voltage regulators, sort of, but they do have a varying reverse voltage. So if you get a 5 volt Zener diode, it's not going to give you exactly 5 volts all the time. The spec sheets generally list a Zener voltage, but it's at a particular test current. If you're away from that test current, you end up with a value that is not exactly the same as the rated value. The symbol looks like this. You'll notice that the Zener voltage is reverse biased and the current is actually going through the diode in the reverse direction. If we look at the characteristic curve in the reverse direction, you'll notice that the Zener voltage is determined at a point kind of down the slope a little bit from where it actually has the knee, and the test current is what determines that. There's also a minimum value you can get, minus VZ0, which is just taken by extrapolating the straight line up to the x-axis. And then if we do need to vary, if the current is different, the slope of that line is going to give us the Zener resistance. And if we have a different voltage and a different current, we can actually determine what the change in voltage is going to be based on what the change of reverse current is. So we can actually use a linear model to replace that Zener diode in reverse with an actual set of resistors and voltage sources. So what we do is we take a voltage source of the value of the minimum Zener voltage, and then we add the resistance, and the total voltage across both the source and the resistance is equal to the Zener voltage. In order to make a voltage regulator, which can be done, one needs to choose a Zener diode with the appropriate voltage, first of all. So if you need 5 volts, choose a 5 volt one. And then it should be operated with the Zener current as close to the test current as possible. It shouldn't vary that much. Also, the load current can't be too much more than a fraction of the Zener current. And that means that we won't be changing the Zener current too much. So the load current is just going to be a slight change or a slight amount of current out of the source current, not a great amount, so that the Zener current doesn't change too much. Now, all that being said, in reality, Zener diodes aren't used so much as voltage regulators because they make integrated circuit regulators that work better. So unless you're on a desert island and really need to build a voltage regulator and you don't have any ICs and you only have Zener diodes, pretty much you're going to be using an IC for this anyway.